The Carnot cycle is a theoretical thermodynamic cycle proposed by Nicolas Léonard Sadi Carnot in 1824 and expanded by others in the 1830s and 1840s. It can be shown that it is the most efficient cycle for converting a given amount of thermal energy into work, or conversely, creating a temperature difference by doing a given amount of work. Every single thermodynamic system exists in a particular state. When a system is taken through a series of different states and finally returned to its initial state, a thermodynamic cycle is said to have occurred. In the process of going through this cycle, the system may perform work on its surroundings, thereby acting as a heat engine. A system undergoing a Carnot cycle is called a Carnot heat engine, although such a perfect engine is only a theoretical limit and cannot be built in practice. Stages. The Carnot cycle when acting as a heat engine consists of the following steps: reversible isothermal expansion of the gas at the hot temperature, T1. During this step the gas is allowed to expand and it does work on the surroundings. The temperature of the gas does not change during the process, and thus the expansion is isothermal. The gas expansion is propelled by absorption of heat energy Q1 and of entropy from the high-temperature reservoir. Isentropic expansion of the gas. For this step the mechanisms of the engine are assumed to be thermally insulated, thus they neither gain nor lose heat. The gas continues to expand, doing work on the surroundings, and losing an equivalent amount of internal energy. The gas expansion causes it to cool to the cold temperature, T2. The entropy remains unchanged. Reversible isothermal compression of the gas at the cold temperature, T2. Now the surroundings do work on the gas, causing an amount of heat energy Q2 and of entropy to flow out of the gas to the low-temperature reservoir. Isentropic compression of the gas. Once again the mechanisms of the engine are assumed to be thermally insulated. During this step, the surroundings do work on the gas, increasing its internal energy and compressing it, causing the temperature to rise to T1. The entropy remains unchanged. At this point the gas is in the same state as at the start of step 1. The pressure-volume graph. When the Carnot cycle is plotted on a pressure-volume diagram, the isothermal stages follow the isotherm lines for the working fluid. Adiabatic stages move between isotherms and the area bounded by the complete cycle path represents the total work that can be done during one cycle. Properties and significance, the temperature-entropy diagram. The behavior of a Carnot engine or refrigerator is best understood by using a temperature-entropy diagram, in which the thermodynamic state is specified by a point on a graph with entropy as the horizontal axis and temperature as the vertical axis. For a simple system with a fixed number of particles, any point on the graph will represent a particular state of the system. A thermodynamic process will consist of a curve connecting an initial state and a final state. The area under the curve will be, which is the amount of thermal energy transferred in the process. If the process moves to greater entropy, the area under the curve will be the amount of heat absorbed by the system in that process. If the process moves towards lesser entropy, it will be the amount of heat removed. For any cyclic process, there will be an upper portion of the cycle and a lower portion. For a clockwise cycle, the area under the upper portion will be the thermal energy absorbed during the cycle, while the area under the lower portion will be the thermal energy removed during the cycle. The area inside the cycle will then be the difference between the two, but since the internal energy of the system must have returned to its initial value, this difference must be the amount of work done by the system over the cycle. Referring to Figure 1, mathematically, for a reversible process we may write the amount of work done over a cyclic process as. Since do is an exact differential, its integral over any closed loop is 0 and it follows that the area inside the loop on a TS diagram is equal to the total work performed if the loop is traversed in a clockwise direction, and is equal to the total work done on the system as the loop is traversed in a counterclockwise direction. The Carnot cycle. Evaluation of the above integral is particularly simple for the Carnot cycle. The amount of energy transferred as work is the total amount of thermal energy transferred from the hot reservoir to the system will be, and the total amount of thermal energy transferred from the system to the cold reservoir will be. the efficiency is defined to be where is the work done by the system, is the heat taken from the system, is the heat put into the system, is the absolute temperature of the cold reservoir, and is the absolute temperature of the hot reservoir. Is the maximum system entropy, is the minimum system entropy. This definition of efficiency makes sense for a heat engine, since it is the fraction of the heat energy extracted from the hot reservoir and converted to mechanical work. A Rankine cycle is usually the practical approximation. The reversed Carnot cycle, the Carnot heat engine cycle described is a totally reversible cycle. That is, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. This time, the cycle remains exactly the same except that the directions of any heat and work interactions are reversed. Heat is absorbed from the low-temperature reservoir, heat is rejected to a high-temperature reservoir, and a work input is required to accomplish all this. The PV diagram of the reversed Carnot cycle is the same as for the Carnot cycle except that the directions of the processes are reversed. Carnot's theorem. It can be seen from the above diagram that for any cycle operating between temperatures and, none can exceed the efficiency of a Carnot cycle. Carnot's theorem is a formal statement of this fact. No engine operating between two heat reservoirs can be more efficient than a Carnot engine operating between those same reservoirs. Thus, equation 3 gives the maximum efficiency possible for any engine using the corresponding temperatures. A corollary to Carnot's theorem states that all reversible engines operating between the same heat reservoirs are equally efficient. Rearranging the right side of the equation gives what may be a more easily understood form of the equation. Namely that the theoretical maximum efficiency of a heat engine equals the difference in temperature between the hot and cold reservoir divided by the absolute temperature of the hot reservoir. To find the absolute temperature in Kelvin, add 273.15 degrees to the Celsius temperature. Looking at this formula, an interesting fact becomes apparent. Lowering the temperature of the cold reservoir will have more effect on the sealing efficiency of a heat engine than raising the temperature of the hot reservoir by the same amount. In the real world, this may be difficult to achieve since the cold reservoir is often an existing ambient temperature. In other words, maximum efficiency is achieved if and only if no new entropy is created in the cycle. Otherwise, since entropy is a state function, the required dumping of heat into the environment to dispose of excess entropy leads to a reduction in efficiency. So equation 3 gives the efficiency of any reversible heat engine. In mesoscopic heat engines, work per cycle of operation fluctuates due to thermal noise. For the case when work and heat fluctuations are counted, there is exact equality that relates average of exponents of work performed by any heat engine and a heat transferred from the hotter heat bath. This relation transforms the Carnot's inequality into exact equality that is applied to an arbitrary heat engine coupled to two heat reservoirs and operating at arbitrary rate. Efficiency of real heat engines, see also, heat engine efficiency and other performance criteria. Carnot realized that in reality it is not possible to build a thermodynamically reversible engine, so real heat engines are less efficient than indicated by equation 3. In addition, real engines that operate along this cycle are rare. Nevertheless, equation 3 is extremely useful for determining the maximum efficiency that could ever be expected for a given set of thermal reservoirs. Although Carnot's cycle is an idealization, the expression of Carnot efficiency is still useful. Consider the average temperatures at which heat is input and output, respectively. Replace Th and Tc in equation by a Euro and a Tca respectively. For the Carnot cycle, or its equivalent, the average value Euro will equal the highest temperature available, namely Th, and a Tca the lowest, namely Tc. For other less efficient cycles, a Euro will be lower than Th, and a Tca will be higher than Tc. This can help illustrate, for example, why a reheater or a regenerator can improve the thermal efficiency of steam power plants and why the thermal efficiency of combined cycle power plants exceeds that of conventional steam plants. See also, Carnot heat engine, reversible process, Carnot cycle graphs should not be confused with Carnot maps in Boolean logic and digital electronics. References: Carnot, Sadi, Reflections on the Motive Power of Fire, Feynman, Richard P. Layton, Robert B. Sands, Matthew. The Feynman Lectures on Physics. Addison Wesley Publishing Company PPA 44 4F. ISBN A0-201-02116-1. Halliday, David. Rusnick, Robert. Physics. John Wiley and Sons PPA 541 548. ISBN A0-471-02456-2. Kittel, Charles. Krummer, Herbert. Thermal Physics W. H. Freeman Company. ISBN A0-7167-1088-9. Kostick, M. Revisiting the Second Law of Energy Degradation and Entropy Generation, From Sadi Carnot's Ingenious Reasoning to Holistic Generalization. AIP Conf. Proc 1411, ppA 327 350. doi, http://dx.org 1.3665247. American Institute of Physics, 2011. ISBN 978-0-7354-0985-9. Abstract at 1. Full article, also at 3. External links: Hyperphysics article on the Carnot cycle. Interactive Java applet showing behavior of a Carnot engine.